let me walk you through the complete mineral processing system, from raw ore, coming out of the mine all the way to high-purity refined metals. This is a full step-by-step explanation of how valuable minerals are crushed, separated, concentrated, and refined using both conventional and advanced technologies. When ore is extracted from the mine, it typically consists of large, irregular rocks, sometimes ranging from 300 up to 500 millimeters in size. At this stage, valuable minerals are still locked inside the host rock, so the first objective is size reduction. This is achieved using a jaw crusher. The jaw crusher operates using compressive force between a fixed jaw and a moving jaw. As the moving jaw reciprocates, it crushes the material against the fixed surface. This reduces the rock size down to approximately 100 to 150 millimeters, depending on the machine setting, initiating the liberation of mineral particles. After primary crushing, the material is still too coarse for efficient separation, so it proceeds to a hammer crusher. Unlike the jaw crusher, which uses compression, the hammer crusher uses impact energy. High-speed rotating hammers strike the material repeatedly, breaking it down further. This reduces the particle size to below about 12 millimeters, or roughly half an inch. At this stage, a much larger surface area of the mineral is exposed, improving the efficiency of downstream processes. Optional double roller crusher can be added after the hammer crusher when finer particle size is required. Once the material reaches this size, gravity-based separation can begin. The first method often used is a jig separator. The jig works by creating pulsating water flow, which causes particles to stratify based on density. Heavier particles such as gold or platinum group metals settle at the bottom, while lighter waste material rises. Following this, a shaking table can be used. The shaking table combines vibration, water flow, and an inclined surface to separate particles. Heavier minerals move in one direction while lighter particles are washed away. At the same time, proper size classification is critical. Vibrating screens and classifiers separate particles by size, ensuring that each downstream process receives optimal feed material. In some cases, especially in arid environments, dry concentration methods are preferred. These include electrostatic separation and dry washer systems. The advantage of dry processing is that it does not require water, reducing operational costs and environmental impact. However, dry methods are generally less effective for very fine particles, and can be sensitive to environmental factors such as humidity. To address these limitations, Avametal has developed a combined system that integrates electrostatic separation with dry washing. This hybrid approach improves recovery efficiency, allows for better handling of mixed particle sizes, and reduces the performance limitations seen in standalone dry systems. Electrostatic separation itself is based on differences in electrical conductivity and particle charge. There are three primary types. The drum type uses a rotating surface, where conductive and non-conductive particles behave differently under an electric field. The plate type, also known as triboelectric separation, relies on particles gaining charge through friction, and then being attracted to oppositely charged plates. The belt type allows for continuous separation using a moving belt system. Each method has its strengths and weaknesses, but by combining drum and plate technologies, Avametal improves overall efficiency and recovery. For finer particles, wet processing becomes necessary. The material is fed into a ceramic ball mill, where it is ground down to approximately 200 mesh, or around 75 microns. The principle here is that finer particles allow better liberation of valuable minerals, which leads to higher recovery rates. However, grinding must be carefully controlled to avoid excessive fines that can complicate separation. After grinding, several concentration methods can be applied. A shaking table may be used again for fine gravity separation. A flotation cell can then be introduced, where chemical reagents are used to selectively attach bubbles to target minerals, allowing them to float and separate from the rest. Additionally, a centrifugal concentrator can recover ultra-fine heavy particles, using high rotational forces that enhance gravity separation. At this stage, the processed material is referred to as concentrate. This means that most impurities have been removed, and the valuable metal content has been significantly increased. However, it is still not pure metal and requires further refining. There are two primary refining approaches. Hydrometallurgical methods use chemical solutions, such as cyanide, to extract metals, but these methods can pose environmental and safety concerns. The alternative is pyrometallurgical processing, which involves high-temperature treatment. In this method, the concentrate is melted together with copper, allowing noble metals to dissolve into the molten copper phase. Following this, electrorefining is performed. An electric current is passed through the molten or dissolved material, removing copper and leaving behind a residue known as anode slime. This slime is highly enriched in gold, silver, and platinum group metals. The final step is electrowinning, where individual metals are selectively recovered from the solution with high purity. Additional processes may also be applied depending on the ore type. Magnetic separation can remove iron-bearing materials. Rotary kilns or autoclaves can be used to treat sulfide ores and remove sulfur before refining. These steps further improve the efficiency and effectiveness of the overall process. There are hundreds of mineral processing methods available, but the key to success lies in combining traditional techniques with advanced technologies. By integrating multiple systems into a unified process, it is possible to achieve higher recovery rates, lower operational costs, and improved environmental performance. This integrated approach represents the future of modern mineral processing.